Q1. You're designing a real-time data ingestion pipeline for a retail analytics platform using Databricks Autoloader. The system must process incoming files incrementally from cloud, storage, and support continuous data flow for downstream analytics. You need to choose the tool that enables Autoloader to perform streaming ingestion and incremental processing. Which tool should be used to support this requirement? A. Checkpointing. B. Spark Structured Streaming. C. Databricks SQL. D. Unity Catalog. The correct answer is B. Spark Structured Streaming. Why this is the right choice? Databricks Autoloader is built directly on top of Spark Structured Streaming. It uses a source called Cloud Files to automatically detect and incrementally process new files as they arrive in cloud storage. How the other options fit into the ecosystem. A. Checkpointing. While absolutely crucial for streaming, checkpointing is a feature used by Spark Structured Streaming to save the state and progress of the stream so it can recover if it crashes. It isn't the overarching tool that enables the streaming itself. C. Databricks SQL. This is used for running SQL queries, building dashboards, and analyzing data after it has already been ingested and structured in your Lakehouse. D. Unity Catalog. This is Databricks governance and data lineage tool used to manage permissions and catalog tables, not to run data ingestion pipelines. Q2. A data engineer is collaborating with a team on a Databricks project that uses Databricks repos for version control. While working on the repository, they need to perform a Git operation that is not supported within the Databricks repos interface and must be executed outside of the workspace using a local Git client or external tool, which Git operation must be performed outside of Databricks repos. A. Commit. B. Pull. C. Merge. D. Clone. The correct answer is C. Merge. Here's why. Why merge must be done outside. While Databricks repos allows you to change branches, pull updates, and commit/push changes, it does not support merging branches directly within the UI. To merge branches or resolve complex merge conflicts, you must use your external Git provider's interface, like GitHub, GitLab, or Azure DevOps, or handle it locally using a Git client before pulling the merge changes back into Databricks. Why the others are incorrect. You can easily commit A, pull B, and clone D, a repository directly within the Databricks repos user interface. Q3. You're supporting a data engineering team that has built an ETL pipeline using Delta Live, table to process travel reimbursement records. The business rule mandates that if an employee's location details are missing, the pipeline must terminate rather than continue processing invalid data. You need to define the constraint behavior to enforce this rule during data ingestion. How can the scenario be implemented? A. Constraint valid_location expect location equals null. B. Constraint valid_location expect location equals null on violation fail update. C. Constraint valid_location expect location equals null on drop row. D. Constraint valid_location expect location equals null on violation fail. The correct answer is B. Constraint valid_location expect location equals null on violation fail update. Why this is correct. In Databricks Delta Live tables, DLT, expectations are used to define data quality constraints. When you want a pipeline to immediately stop and terminate execution upon encountering invalid data, you use the on violation fail update clause. Here is how the syntax breaks down for your exact business rule. SQL constraint valid_location expect location is not null on violation fail update. Note, while is not null is a standard SQL syntax for checking nulls, fail update is the exact operational keyword combination DLT uses to halt the pipeline. Why the other options are incorrect. A is incorrect. The condition location equals null would actually fail everything, and checking the quality with null in SQL returns null, not true. Additionally, it lacks a violation action, which defaults to just logging the metrics rather than stopping the pipeline. C is incorrect. On drop row is invalid syntax. The correct keyword for dropping a row is on violation drop row, which would silently discard the bad record and keep running. Violating the rule to terminate the pipeline. D is incorrect. On violation fail is incomplete syntax. Delta Live table strictly requires the full fail update keywords to specify that the entire pipeline update should fail. Q4. A DevOps lead at a tech firm is overseeing a Databricks SQL query that tracks system metrics for a newly deployed application. To ensure real-time visibility, the query is scheduled to refresh every minute during the first week post-launch. The lead wants to avoid unnecessary cloud spend once the monitoring period ends. What configuration should the team apply to prevent the query from incurring costs after the first week? A. Configure a cap on the number of DBUs allocated to the SQL endpoint. B. Define a refresh schedule that halts after a fixed number of executions. C. Set an expiration date for query's refresh schedule using the query scheduler. D. Restrict the number of users who can modify the query's refresh schedule. The correct configuration to achieve this is C. Set an expiration date for the query's refresh schedule using the query scheduler. Why this is correct? When configuring a scheduled refresh in Databricks SQL, the scheduler allows you to specify a clear time frame for execution. By expanding the advanced options under the Query Schedule menu, you can explicitly set an expiration date. Once that date passes, at the end of the first week post-launch, the schedule automatically becomes inactive, preventing the query from continuously waking up the SQL warehouse and running up unnecessary cloud costs. Why the other options are incorrect. A is incorrect. Capping DBUs handles maximum concurrency or sizing parameters for the SQL warehouse, but it will not stop a query from running every minute indefinitely. It would just limit the performance capacity while continuing to consume costs. B is incorrect. Databricks SQL query scheduling is based on time intervals, frequencies, and specific calendar dates, not a static count of a fixed number of executions. D is incorrect. Restricting who can modify the schedule is a security and governance measure access control, but it does nothing to automatically stop the current active 1-minute schedule from running. Q5. A data analyst has built a Delta table named Sales that is actively used by the analytics team. To validate the data quality, they request support from the data engineering team, which prefers working in Python using PySpark. The engineers need to access Sales in PySpark to begin writing validation logic, which command allows the data engineering team to access Sales in PySpark. A. Select asterisk from Sales. B. Spark.table Sales. C. Spark.SQL Sales. D. Spark.delta.table Sales. The correct answer is B. Spark.table Sales, noting the minor typo in the option quotation marks, which should be consistent. Why this is correct. In PySpark, the Spark.table method is used to read a registered table or view from a Hive Metastore or Unity catalog into a data frame. Since the Delta table Sales is already active and being used by the analytics team, it is registered in the catalog, making Spark.table Sales the standard and most direct way to load it. Why the other options are incorrect. A. Select asterisk from Sales. This is standard SQL syntax, not Python/PySpark code. C. Spark.SQL. Sales the Spark.SQL. Method expect to complete valid SQL query string, e.g. Spark.SQL. Select asterisk from Sales. Passing just the table name will result in a syntax error. D. Spark.delta.table. Sales, this is not a valid PySpark API command. While you can read Delta tables using Spark.read format, Delta.load path, the Spark.delta namespace does not exist for loading tables this way. Q6. You're part of an IT infrastructure team evaluating the classic Databricks architecture for A. Secure analytics deployment. To ensure proper separation of compute and management layers, you're asked to identify which component is hosted entirely within the control plane Which option correctly reflects this? A. Worker node. B. Databricks web application. C. Driver node. D. Databricks file system. The correct option is B. Databricks web application. Explanation: in the classic Databricks architecture, there's a strict separation between control plane and the data plane. The control plane is hosted in Databricks' own cloud account. It contains the back-end services that manage the environment. The Databricks web application, the user interface, notebook manager, workspace security, and job scheduler, resides completely within this control plane. The data plane is hosted within your company's cloud account, e.g., AWS, Azure, or GCP VPC. This is where your actual data resides and where processing happens. Why the other options are incorrect. A and C. Worker and driver nodes, these form the compute clusters that process your data. Because they need direct access to your data sources and must comply with your internal network security rules. They are deployed entirely in the data plane, your cloud subscription. D. Databricks file system / DBFS. The underlying storage for DBFS is an object storage bucket, like an AWS S3 bucket or Azure ADLS Gen 2 account, that lives inside the customer's own cloud subscription data plane, not the control plane. The correct option is B. Databricks web application. Explanation: in the classic Databricks architecture, there is a strict separation between control plane and the data plane. The control plane is hosted in Databricks' own cloud account. It contains the back-end services that manage the environment. The Databricks web application, the user interface, notebook manager, workspace security, and job scheduler, resides completely within this control plane. The data plane is hosted within your company's cloud account, e.g., AWS, Azure, or GCP VPC. This is where your actual data resides and where processing happens. Why the other options are incorrect. A and C. Worker and driver nodes, these form the compute clusters that process your data. Because they need direct access to your data sources and must comply with your internal network security rules. They are deployed entirely in the data plane, your cloud subscription. D. Databricks file system / DBFS. The underlying storage for DBFS is an object storage bucket, like an AWS S3 bucket or Azure ADLS Gen 2 account, that lives inside the customer's own cloud subscription data plane, not the control plane. Q7. A data engineer manages a Databricks job with a detailed execution schedule involving multiple time-based triggers. To replicate the schedule across other jobs without manually configuring each field in the UI, they want to find and submit the schedule using a programmatic format. What tool or syntax should they use to represent the schedule? A. PySpark.SQL.types.datetype. B. Datetime. C. PySpark.SQL.types. Timestamp type. D. Cron syntax. The correct option is D. Cron syntax. Explanation: when defining a Databricks job schedule programmatically, such as via the Databricks Jobs REST API, the Databricks CLI, or Terraform, Databricks uses a standard Quartz cron expression to represent complex, time-based triggers. A cron string allows you to explicitly define multifaceted execution patterns, e.g., run at 10:15 a.m. every Monday through Friday, in a single compact line of text that can easily be copied and pasted across multiple job JSON definitions. Why the other options are incorrect. A and C, date type and timestamp type. These are PySpark SQL data types used to define the schema of columns within a data frame. They have nothing to do with job orchestration or task scheduling. B. Datetime. This is a standard Python library module used for manipulating dates and times inside your code execution. While you can use it to fetch the current time, it cannot be used as a configuration syntax to define recurring triggers for the Databricks job scheduler. Q8. A data engineer working on a retail ingestion pipeline uses autoloader to process JSON files without supplying any schema hints or type inference logic. After loading the data into a target table, they observe that every column is stored as a string even though some fields contain only float or Boolean values. What explains this behavior in autoloader? A. The expected schema and the detected schema had conflicting data types. B. The JSON source uses a format where all values are stored as text. C. Autoloader supports only string columns during ingestion. D. Each field had at least one null entry, affecting type detection. The correct option is B. The JSON source uses a format where all values are stored as text. Explanation: by default, when you use autoloader cloud files to ingest JSON data without providing a schema or enabling schema inference, autoloader needs to safely handle the incoming data. However, if autoloader is intentionally configured to infer schemas, it will correctly identify floats, integers, and booleans, unless the source JSON files themselves wrap all those values in quotation marks, e.g. price, 19.99, or is underscore active, true. If the underlying JSON text physically wraps every single primitive value in quotes, the JSON parser reads them strictly as literal string values. Why the other options are incorrect? A is incorrect. If there were conflicting data types across files, e.g., a float in one file and a string in another, and schema inference was active, autoloader would trigger its schema evolution behavior. By default, it would either cast to a compatible type or place the conflicting data into a rescue data column, rather than universally forcing every single clean column to a string. C is incorrect. Autoloader natively supports all standard primitive and complex data types, integers, floats, timestamps, booleans, maps, arrays, etc. during ingestion. D is incorrect. Autoloader easily handles null values. In Apache Spark and Delta Lake, a null entry does not force an entire column to a string data type. Columns can easily maintain a float or boolean type while containing nulls. Q9. A data engineer is working in a Python notebook in Databricks and needs to execute a SQL query for a particular transformation. They want to use SQL within a cell of their Python notebook without modifying the rest of the notebook, which continues to run Python code. The engineer is exploring how to embed SQL logic in a single cell. Which of the following describes how the data engineer can use SQL within a cell of their Python notebook? A. It is not possible to use SQL inside a Python notebook cell. B. They can connect the cell to a SQL endpoint instead of using a Databricks cluster. C. They can enter SQL statements without any language declaration. D. They can begin the cell with %SQL to enable SQL execution. The correct option is D. They can begin the cell with %SQL to enable SQL execution. Explanation: Databricks notebooks support magic commands, which allow you to override the notebook's default language, in this case Python, for a single cell. By placing %SQL at the very top of the cell, you instruct the Databricks notebook interface to interpret and execute that specific cell's entire contents using the SQL execution engine. The rest of the notebook remains completely unaffected and will continue running Python code. Why the other options are incorrect? A is incorrect. Mixing languages using magic commands is one of the core collaborative features of Databricks notebooks. B is incorrect. While Databricks SQL warehouses, formerly SQL endpoints, execute SQL, you do not switch the connection of an individual cell to a different compute resource to change languages. You change the language handler using magic commands. C is incorrect. Because the notebook's primary language is configured as Python, trying to write raw SQL statements without the %SQL magic command will cause the cell to throw a Python syntax error. Q10. A newly onboarded data engineering team has been added to an enterprise workspace and assigned to a project involving the customer's database. To begin their work, they need visibility into the existing tables within that database. The team is part of a workspace group named Team. What command should be used to ensure the group has the correct permission to explore the database? A. Grant view on catalog customers TO team. B. Grant create on database customers TO team. C. Grant usage on catalog team TO customers. D. Grant usage on database customers TO team. The correct option is D. Grant usage on database customers TO team. Explanation. In Databricks Unity Catalog and standard data governance models, permissions follow a strict hierarchy. Catalog $right to a schema /database $right to a table. To allow a group to see, explore, or interact with any objects inside a database, they must first be granted a usage privilege on that specific database. Without usage, users cannot browse the database or access any of the tables within it, even if they have direct permissions on the tables themselves. Why the other options are incorrect. A is incorrect. View is not a valid privilege for a catalog in Unity Catalog. To look at a catalog, you would use grant usage on catalog. Furthermore, the question states that customers is a database, not the catalog. B is incorrect. Grant inquiry allows the team to build new tables or schemas inside the database, but it is an excessive administrative permission if their immediate requirement is simply to gain visibility and explore existing tables. C is incorrect. The syntax is reversed. It attempts to grant permissions on a catalog name team to a user/principal named customers.